The objective today is to solve small world problems that require reasoning about file sizes. So the 8-bit byte has become the de facto fundamental unit with which we measure the size of data on computers, and in fact today most computers only let you save data as combinations of whole bytes. So even if you only want to store 1 bit of information, you have to use a whole byte to do it. Many computer systems will require you to store even more than that, actually, and messages sent over the internet are also typically structured as messages with byte offsets. So you may, in transmitting a message, you may have, chunks like this, 8-bit chunks called a byte. Okay, so that last part was very important for you to remember, okay? Byte offsets is a great way to wrap your mind around the immensity of a computer. Of course, you would need a byte offset for a simple message in ASCII. So digital storage, 1 kilobyte is actually 8,000 bits. Okay, and so if you don't know what a byte offset is, here we go. A byte offset is the number of bits from the base address. So for example, the 2 words, if I was going to, it's a little strange, but ask for an offset of just 2 words like hello bats, this has an offset of 9. So starting at 0 right here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from the base, from the beginning, it has an offset of 9. Think right here, what is the offset of your first name? And so in ASCII, the number 75 is actually 65, sorry. 65 is A. Well, we need zeros to make a sizable offset before a bit shows up for the first time. What I'm saying is right here, A is 65. You see a 0, then it says 1, 0, 0, 0, 0, 1, okay? That 0 right here is called padding, so there's just a single padding right there, and then the first bit shows up. How much padding is there for a lowercase a? Right here, it's actually the same amount of padding as the uppercase a. So you'll notice a pattern right here. There is a single 0 in the beginning of every ASCII number. Why do you think that is? Okay, let's get really fancy here, and don't freak out over all this code. Let's just divert your eyes to the right-hand side of the screen. Byte offset 0. So this is the beginning right here. We know it's a hexadecimal because it's a 0x. So here's 1 nibble, another nibble. 2 nibbles make a byte. So 15 is the first byte. 2 is the second byte. So right here, the offset is 2 bytes. First byte, second byte, third byte, fourth byte. Okay, there it says 4. There's the 5th byte, and then there's not another byte here, so then the offset's only 5, and so on. Big numbers we're talking about. We've been working in such a small microcosm of the actual computer. So now let's try to wrap our mind around these big numbers. Paralleling the explosion of computing power and speed, the sheer size of the digital data now created and consumed every day is staggering. The implications of so-called big data will not be investigated until later in the course, but it's good and interesting to be thinking about the size of things now. All or nothing. Bytes become the fundamental unit with which we measure the size of data on computers, and in fact, today, most computers only let you save data as combinations of whole bytes. Even if you only want to store 1 bit of information, you have to use a whole byte to do it. Recall in previous lessons, Unit 1, Sending Formatted Text, we learned that in addition to the actual text of a document, it is usually necessary to store the formatting information that allows the text to be displayed correctly. Just like the formatting in this thing I'm reading right now, it is red, so that's a different type of formatting than the text that's above it. We might wonder just how much extra information, that is, how many extra bytes we need to store when we include all of this formatting. Well, let's find out. If a single ASCII character is 1 byte, then if we were to store the word hello in a plain ASCII text file in a computer, we would expect it to require 5 bytes, or 40 bits, of memory. What about a Microsoft Word document that contains the single word hello? Think right here, predict how many more bytes will a Word document require just to store the word hello than a plain text document. Here are some files you can download to use. It says plain text document hello.txt and MS Word document hello.docx. Now you can create these yourself right there on your computer. Open up Microsoft Word, type in hello, save it as hello.docs, and you're done. Open up Notepad, save that file that says hello by saying hello.txt in the save as box, and you got it. So to find the actual size of the file on your computer now, do one of the following. If you're on the PC in Windows, which most of you are, right-click and choose Properties of that file. In general, the Word doc should be thousands of times larger than the plain text. For the files above, we're looking at something like 5 bytes compared to 21,000 bytes. And if you don't believe me, you can go through these steps, okay? So some think right shares in terms of manipulating these file sizes in your mind. Let's start with the first one. Alice has 600 megabytes of data. Bob has 2,000 megabytes of data. Will it all fit on Alice's 4 gigabyte thumb drive? Number 2, Alice has 100 small images, each of which is 500 kilobits. How much space do they take up overall in megabits? So you can do a conversion here and use a formula just like you would in any other mathematical conversion. It says here gigabytes equal megabytes divided by 1024. The formula to convert from gigabytes to megabytes is gigabytes times 1024. Pretty easy to remember. So here's a fun fact. A 5-byte file is so small that some computers won't allocate a chunk of memory that small. For example, you might see something like this. Kind, plain text, document, size 5 bytes, but on the disk you'll see 4 kilobytes. Which indicates that even though the file is 5 bytes, it's taking up 4 kilobytes of memory on your computer. Time for the DOL here, and I'm recording this around Halloween. I wonder what time of the year it is that you're watching this, but nonetheless, here is our small world problem to solve. Number 1, your ghost hunting group is recording the sound inside a haunted classroom for 20 hours as MP3 audio files. About how much data will that be expressed in gigabytes? And number 2 directly connects to the description of our DOL here with at least greater than 5% improvement. What would be the first step in compressing an audio file? And I'll give you a hint here. You have this recording inside of a classroom that I presume is empty if you're trying to catch the ghost. You're in this classroom, and for 20 hours it's recording. Think about the pattern that you may have and that you can then compress into a representation. And by answering number 2 correctly, simply what would be the first step in compressing the audio file, you should easily jump way above 5%.